Good evening. Today we are going to see the syllabus for Insem examination. So we have this first theory and singly reinforced section. So theory of singly reinforced and general we are going to say it. So now we will start with the limit state method. We have assumptions of this. You have this in IS 456 2000 page number 69. So I will not go in detail with this one. You can with IS code, but if you are going to write down in examination, write in your words. Now we have to go for stress block parameters, and for stress block parameters, we are going to use this curve. I will go a little bit fast. I have prepared the presentation, and so with that we can cover the portion fastly. So we are going to cover this part, and you can see this. We have 0.67 FCK upon gamma m, and gamma m we have 1.5, and this value approximately come as 0.446 FCK. We have this rectangular portion that is 0.002 to 0.0035, and from 0 to 0.002. So now we can have this as strain diagram. If we will see in assumptions, then we have the maximum strain in tension reinforcement, and we have this value that is 0.002 plus Fy upon 1.5 ES. So we have that value. So you can see this. So we have this strain, and that value we are going to be with IS code. You can go with IS code. So it is 0.002 plus Fy upon 1.15 ES. As we have seen, we have to go to page number 69, and on page number 69, this value is given. So 0.002. So though it is written over here, that is Fy upon 1.15 ES. So here actually it is 0.002. And then we have this, we have seen this 0.002 till 0.002 strain. We are going to be diagram. You can see this 0 to 0.002. We have parabola portion, and above this we have rectangular portion. So this is 0.446 FCK. So it is approximately taken as 0.45 FCK. So maximum strain in concrete 0.0035, and that is at the junction of parabola and rectangle, we have 0.002. We have this as neutral axis, and we are interested this distance 0.002. Then we are going to be use geometry. This already we have seen. I will not go in detail. And we are going to get depth of parabola as 4/7 XU and depth of rectangle as 3/7 of XU. So when you will go for stress block parameters, you have to draw these diagrams. So you have to start for stress block parameters from here. If you will not show this geometry portion, then also it's okay. You can directly write it 3/7 XU and 4/7 XU. Then compressive force, we know that is total area of this stress diagram into width of the cross section. That will gives me compressive force. So area of stress diagram, we have this as parabola and rectangle. So we have these values 0.45 FCK 37. So this will be first value, which is of rectangle. And then second value we have that is of parabola, which is 2/3 of 0.45 FCK into 4/7 XU. And this is width of the beam. And from this we will get these values, that is approximate that value 0.364 FCK XUB. So we will take this 0.36 FCK XU into B. So this is our compressive force C. Then we will go to the position of compressive force. So these two parameters we require when we will talk about stress block parameters. So we are interested to find a position of this C, and then we have x bar summation A x bar upon summation A, and then area of rectangle into x bar from top plus area of parabola into x bar from top, and then area of rectangle plus parabola. This already we have seen, which is 0.36 FCK XU into B. So now you can see we have area of this first, we have 0.193 FCK into XUB. These values actually we are going to take First value we have 0.193 FCKXU, second value 0.171 FCKXU. That values we have taken over here. Now centroid of this rectangle will be half of 3/7 XU, and this parabola we have this will be 3/8 from here. So we have this value 3/8 of 4/7 XU, 3/8 of 4/7 XU, and then we have to add this value that is 3/7 XU. So we will get total value from top, that is 3/7 XU plus 3/8 into 4/7 XU. You solve it once because when we are going to see it, we will think that we can do it. But if in examination, if you have this question, then you should be in position to solve this. And then by solving this, you will get value of x bar 0.42 into XU, and this will be from top. So my compressive force will act, that is just in rectangle, and that will be value 0.42 XU. So these two we require when we will talk about stress block parameter. Then neutral axis, these things are not required. You have to find out value of neutral axis, that is XU, x bar 0.42 XU, and C. These two values are expected in stress block parameters. Now neutral axis calculations that we know, we have compression equal to tension, and tension we have again for stress into area. Now when we will talk about stress, then we have that is Fy upon factor of safety and into area of steel. And factor of safety we have for this steel, we have that value 1.15, and therefore this value is taken as 0.87 Fy AST. And then we have this value, and from this we are in position to find out value of XU. That is neutral axis calculation. Then we have moment of resistance calculation. So we know formula, we have force into lever arm. So Cu into lever arm or Tu into lever arm. I will not go in much detail with this. So this value already we have seen. We have this is stress block parameter, and this is lever arm distance between the two forces. You can see we have this D minus 0.42 XU. And or we have 0.87 FIAST lever arm, we have same for both. Then so when we have both materials reaches the maximum value simultaneously, that section we are going to say as balance section. And from this we are going to becomes XU equal to XU max, and we are going to be with these values. And then if we will solve this, already we have taken in the class. So we have 0.0035. Just we have taken this as similar triangles. XU max upon D minus XU max, and that is equal to 0.0035 upon 0.002 plus Fy upon 1.15 ES. So this one triangle we have taken, and this another triangle we have taken. And then we have rearranged the terms. We have taken ES, that as LCM, and from this we will have this 0.0035 into, if we will write one step, then you have 0.0035 into ES divided by 0.0055 into ES plus 0.87 Fy. And then if we will put ES, that is 2 into 10 raised to 5, then we are going to get this value 700 upon 1100 plus 0.87 Fy. Then critical neutral axis. So we are just going to put a value of Fy in this. So first we have substituted 250. So we will get 0.53. These values are in IS code. You can go page number 70. You will get these values. So for 415.48 and for 500, we have 0.46. Then moment of resistance factor. So I will not go again in detail with this one. So we have moment of resistance, and we will convert XU into KU max into D, and from this we will get RU max BD square, and from this RU max is 0.36 FCK KU max 1 minus 0.42 KU max, and RU max is known as critical moment of resistance factor. Then area of reinforcement. So I will not go in this derivation also you not required, but you should know how it will be derived. And from this we are going to be with AST, that is percentage PT, and we have this value. This formula you require 0.5 FCK upon Fy in bracket 1 minus root of 1 minus 4.6 RU into FCK. Just you have to remove MU and you have to put RU, and BD we have to cancel because we will take that is in denominator, and likewise we have to find the value of percentage of steel. If you have to find out balance, then you have to make Ru that is equal to Ru max only, and that will gives you PT balance. For PT balance, you have to make this Ru that is equal to Ru max. Design parameters. So if we will calculate the values, then we are going to be these maximum values. So just I have prepared this table. You can cross check it, and from this you are going to get this value, because this Ku max actually we have 0.53, 0.48 and 0.46, and these are same for all concrete grades, because this depends only on grade of steel. And then just substituting the values, we can prepare these design parameters for a balance section. Now we will go with the problem. So we have first the dimension of a rectangular. So I have mostly solved all the problems which are in our question bank. So we have 250 by 300 and clear cover 25 and 3 bars of 16. So try to understand this. We have clear cover that is 25, and then in that case what will be my value of D? So we have this will be 16 mm. So till bottom we have this value as 25, and D we have always till the center of this, and we have this as 16 mm. So this will be 8, and therefore we have D dash that is effective cover, and we have effective cover that is 25 plus 25 plus 8, and we have that will be 23 millimeters. So we have this D dash that is 23 millimeters. Sorry, 25 plus 8, 33 millimeters. 25 is clear cover, 8 we have half the diameter, and that will be 33 millimeters. So now you can see this. So we have D 300 minus 25 minus 8, and from this we have, so in examination it should be systematic. So whatever given data you have to write down it and then use the formula. Here we are interested the percentage of steel provided. So we know AST upon BD into 100, that will be percentage PT, percentage steel we can have. And then we have substituted these values, and from this we will get this value at 0.9%. Then we have second, we are interested to find the balance percentage of steel. Then again, first go for given data, and already I mentioned it. If we have to go balanced, then we have to make it as balanced, and in that case, we have to use this as max. And therefore, we have calculated Ru max 2.76, which we will substitute in PT. So 0.520 upon 415, and here we have that is Ru max, and that will gives me balanced or maximum percentage of steel 0.95%. Then we have beam 300, effective depth we have 365, and we are interested to find the area of steel in a balance section. So in this we need not require to worry about it. Whenever we will say balance section, so we have XU equal to XU max. That we have to keep in mind. Here AST we have to find out for balance, means we have section that is balance section. And for balance section, we should have XU equal to XU max. And then we can have this value that is 0.36 FCK XU max. So we have same 2.76 percentage still just we have calculated, which is 0.95%. And then we have AST upon BD into 100 as 0.95, and AST we will get 0.95 upon 100 into BD will go on right side will be 300 into 365. That will gives me value that is 1040.25 millimeters square. Then we have a concrete beam 300 mm wide, 420 mm effective depth, M20 and Fe415. Find the depth of critical neutral axis. Actually, this depth we have always from compression side. So we have one example. Find the depth of neutral axis from compression side. So that will be same. So no change. That is only depth of critical neutral axis. And then we have this D for 20 millimeter that is given, B is given 300, and we are interested to find out XU max, and we will get value of XU max that is equal to 201.6 millimeters, because we know actually you can directly go for Fe415. We have this value Ku max at 0.48, and just we have substituted that value. We are going to get then this value that is XU max. Then we have determined the design constants. So now this design constant, we know we have one thing, we have neutral axis factor Ku max, lever arm factor, we have Ju max or J max, and moment of resistance factor, we have Ru max. And then we will have this as Fe415. Then again we have Ku max as 0.48. Then we have Ju max, that is 1 minus 0.42 Ku max 0.8. And Ru max we have 0.36 FCE Ku max 1 minus 0.42 Ku max. And then we have substituted this Ku max and this is Ju max. Gives me value 2.76 Newton per mm square. Now we have some examples where we are going to calculate the moment of resistance due to steel is equal to. Now due to steel we have to find out. So we will go first with given data. Once we have this given data, that is given as 3 bars of 20 mm diameter. So we have diameter of 1 bar is 314.16 and AST we will have 942.48 millimeters. Then from this, because we know we have formula that is 0.36 FCK XU into B, and that is equal to 0.87 FY AST. And from this we can find value of XU, and that is 0.87 FY AST. And this portion 0.36 into B will go in denominator, and that we have used, which will give me 157.54 millimeters. Then Ku max we have 0.48. Already we have taken this problem in class also, and which will give me value of moment of resistance as 101.69 kilonewton meter. Then we have here that is moment of resistance. So here we have calculated actually moment of resistance due to steel. If anyone calculate this value by using concrete, then also you will get value same. You can go by this 0.36 FCK B into XU max in bracket lever arm we have as it is D minus 0.42 XU max. We will get same value, but as they have asked by steel, therefore we have used this steel formula. Then we have a rectangular section and we are interested the moment of resistance due to steel again. So we have same problem. So now in this we have XU to 10.05 millimeters. So now same we have used that is 0.36 FCK XU into B equal to 0.87 FIST. Now here you can see in last you have to keep in mind, this is most important. In last problem we have that is XU max, which is greater than your value of actual XU. This is XU actual, and this XU actual, this value is less than XU max, and therefore we have under reinforced and then we have calculated value. But here if we will see, then you have this value, this is XU actual, and this XU actual value which is greater than XU max, and in that case we cannot go beyond maximum value, and therefore section is over reinforced and we have to limit XU equal to XU max, and therefore we are now using formula as XU max. You can see for over reinforced we cannot go more than XU max, and therefore in over reinforced we are using XU max, and in under reinforced we are going to use value of XU. You can see here we are using XU. That is the major difference you have to keep in mind. Under reinforced XU and over reinforced we have XU max. For balanced also we have XU max value and we have this value 110.28. Now you can go with this. Now here it is asked that is the moment capacity. Moment capacity again means we have balanced section because it will give maximum capacity, and moment capacity expectation is maximum, and therefore we have XU equal to XU max. I have used same problem so that you will be in position to understand, and the section is balanced, and therefore we are going to use XU equal to XU max. In when over reinforced we have same, and in balance also we have same. So over reinforced, for over reinforced sections my capacity is equal to capacity of balance section. So these are the things which are from your first part, that is singly reinforced section. So thank you. We will stop for first part here only. So then we will go to the next part. Thank you.